I don't know. I have the volume turned down. I don't. Okay, so whenever you're ready. Okay, so.
See, that would have been rude.
Any other time? Oh, I would have been smiling underneath the mask when I said that.
I know you would have.
All right. So far, all we have talked about is direct current. That's always where the current is flowing in one direction. Now we're going to look at what is more common, because it tends to be easier to produce on a large scale, which is direct current. Because what happens when you spin a magnet near a coil of wires is when it's facing one way, it starts pushing current one way, and when it flips around the other, it pulls it back. So you end up with this pushing and pulling of current, and you get this alternating current that ends up occurring. So what we're talking about here, we're not going to talk about all of this. We're not going to do inductors in an AC circuit. So that's out, that's out, that's out, and that's about it. So we're going to start with alternating voltages and currents, and we'll talk about capacitors in them and whatever. So we're going 2, 1, 2, 4. So anything in the anything in that practice set I put up that has inductors in it, just ignore. I'm not going to cover the inductors. Is there, well, I guess I'll ask that at the end. Remind me to ask that a minute about what we wanted to do with the homework from 24. So here we can have something very simple. Example is just a wall outlet, 120 volt alternating current circuit, and it provides current and voltage, and they vary sinusoidally. So we can describe this with sine functions, which should make sense because, as we talked about before, things that are going in circular motion are described by sinusoidal stuff, right? It was just in both directions, like parameterized of it. And we're creating current typically by spinning giant magnets. So we end up with this sinusoidal type of alternating current. Is it the only type of alternating current we can get? No, it's not. But it is the one that we tend to see the most coming out of the wall. All right, and it'll look something like that. So this is the one we're most interested in. Voltage is just the maximum voltage times the sine of omega t. Remember, omega is 2 pi f, so that's our angular speed or angular velocity. Okay, and so you could also write this as equals V max, which is your amplitude, sine 2 pi ft. So it's based there on the frequency of it. Where again, that's V max, and then this down here would be like negative V max. Okay, and it's going to alternate in between those as the amplitude is right out there in front of your sine function. If it's a circuit that has only one resistor, then we can also just very easily use our Ohm's law to come up with an equation for the current. It's going to pretty much just go right along with it. I equals V over R. This time we're going to do V max because our voltage varies. We just end up with whatever the voltage happens to be over R is what the current will be. So the current will go up and down with it. So if we look at our maximum voltage over R times the sine of omega t, that's V max. That is what our voltage is. So in other words, we can say it's like this, like this is voltage as a function of time, and this is current as a function of time. And so the voltage as a function of time is that V max times sine of omega t, plug it in, and then we can just say that V max over R is our maximum current, because when we have the maximum voltage is when we're going to get the maximum current. And so there we go. Just to write it once here for you, I as a function of t is I max sine omega t. Sorry, I kind of crammed it over onto there. Sine omega t. Okay? So as you can see, they're going to vary in phase with each other. As the voltage goes up, the current will go up, all right, for just through a single resistor. As the voltage goes down, the current goes down, and they're going to just mirror image right on top of each other, okay? So they are in phase. All their peaks and everything are all in phase. When one of them 0, the other is 0 as well. This will not be the case for capacitors. All right, in order to visualize this, we can have these phase diagrams. And essentially the idea is we simply have a vector that has a length equal to the maximum voltage or the maximum current, and it rotates around in a counterclockwise direction with an angular speed of omega, all right, our angular frequency omega. And at any moment where we take the projection of that vector onto the y-axis, that will tell us the amount of voltage or current at that single time. It's essentially, it's just a projection. That's that sine of omega t. It's that component of it, right? Remember, whenever we wrote out, if we wrote out any kind of a vector, we can always say, like here's vector v. We can always say, we have this x component and we have this y component. The x component is v cosine theta. This one's v sine theta. And so we're taking that sine theta, which is theta is just omega t. So we're taking that times that, and that tells us the projection of it onto the y-axis. So as it rotates, that amount that it's in the y direction varies according to the sine, and you get different amounts of it. The nice thing about this is you can see here, when we do this, you can see that the voltage and the current there are in phase with each other. They're always going to stay lined up and rotate together. They'll have different lengths, but they're going to rotate together. Okay? And so this essentially, like this over here is, this is I of t. It's your and this is v of t. Okay? Does that make sense to y'all about the projection? So if V max is like over here, then the voltage is this amount right there. If V max is down here, then you trace over and say, all right, here's the current voltage. And if it's over here, then the current is, or the current voltage is 0. Okay? Does that make sense? Oh, I see a scrunched up face there. What's up?
Just, well, I mean, I'm just still trying to understand what this graph is telling me. I don't know. I'm a little lost.
So remember that circular motion, if we only look at just the x part of it, like if I want to create circular motion, I can make something that like, how do I say this? Let's say I wanted to make a robot arm that could draw a circle. I would give it 2 axes to move. I'd give it like a little track to move this way, and then I'd hook that track on another track that makes it move this way. And what I would do is just plug in a sine to both of them. And so as this one starts to move up, this one starts to move this way. And then this one gets to its maximum and starts to come back down while this is moving up, right? And then this one will start coming back this way as this one continues going left, and it'll make a circle, right? So if I'm just looking at one direction, like even though I'm going in a circle, all you can see is it just looks like it's going back and forth, right? That's the projection of it into that. So what we're doing is we're taking this and we're simply projecting it into the y-axis. So right here, this would be 0 voltage. The voltage is increasing. There's the maximum voltage. Now the voltage is decreasing. Now the voltage is 0. Because it's the length of however long the pin looks to be to you where you are, because you're taking that projection. So that's what it's showing you. It's a nice, easy way to show how in or out of phase they are, and also allow you to figure out what the actual current values of each are. So these would be rotating. These rotate, and as they rotate, these projections on the y-axis change lengths. So right here, they're the length they are. When they get here, they're both fully in the y direction, it's maximums. When they get over to here, they're both 0 in the y direction, so the voltage and current is 0 at that moment. and then maximum in the negative, and then it comes back around to 0. You're just always taking that projection over. Yeah. Why do we have alternating current? This was a big giant debate back in the day, which we should have. And what's his name? Tesla won this. He was in favor of the alternating current. Essentially, it's just very easy to make. It's a lot easier. You spin a magnet and it just makes alternating current. And that's typically the way we make it.
So alternating, you mean it goes up and goes down like the side.
Like the current will come one way and then the current will go the other. And then one way and then the other.
So, yeah, I just don't understand why. Like, why is that easier than just looking to a constant?
Okay, tell me how you're going to make a constant one-way volt current. How? With a battery? That's chemically, right? It's like what we were doing before where it was chemically done. We had, a chemical that wanted to get rid of electrons and a chemical that wanted to gain them, and we gave them a path, and that's the way it went. So if you were going to make direct current for all households, you'd have to make a giant battery and keep recharging that battery somehow. If you're going to actually make current from like other types of energy sources other than just chemical, like you end up spinning a magnet. And so where do I have room to draw? And so what you have is, let's say you have a coil of wires here, right? Here's our coil of wires. Okay. And we have a magnet here. And if I push this magnet towards it, it causes a flux change in one direction and makes the current flow one way, right? So let's say it makes the current flow this way. Then if I pull the magnet away, then it changes a flux in the opposite way and the current flips and goes the other way. So that does that. If instead of moving it like toward and away like that, I can spin it. When this side, let's call that north, let's say when this side is over here, it causes current this way, but when the south side spins over and gets over there, it's going to make it go the other way. So these all cause alternating currents. Maybe I could do something fancy where, like, say instead I took and made like a ring magnet. Didn't mean to highlight there. Maybe I made like a circular magnet, right? With all the magnets pointed in one direction. I don't know, I just had this idea. But then as it would spin through there, there'd be no changing in flux and I wouldn't get any more current. So this would produce no current for me. It has to increase and decrease. You have to change it. So I can either create current by forever ramping up the magnetic field, which is impossible, or I have to alternate. I have to ramp it up and then down and then up and then down. That I can do. Because once it stops changing, I can't just put a magnet on it and leave it, because then it'll make a little bit of current and then it'll stop. It has to be constantly changing. So I can change it all the way up to infinity, which I can't do, or alternate it. Is that what you're asking me? Is that?
So you don't have to like recharge it.
You're not recharging it, but you keep having to put energy in to spin the magnets because there's a drag, like I asked that question about the satellite in space with the giant loop out there, the giant tether that would move around through the magnetic field and generate electricity. And I said, this is actually not free electricity. Anybody ever figure out why? Because it'll create drag, because the magnetic field is created to oppose Earth's magnetic field, and therefore it creates drag and slows the satellite down. If it slows down, it starts to come out of it starts to fall. It starts to go down towards the planet. So if you were going to do that, you'd have to, every once in a while, you'd have to re-put yourself back out further, because eventually it would make you fall down into the planet. You lose altitude. You're losing potential energy, essentially. Okay, and the same thing here. If you just started it spinning, it would stop. There would be a resistance to it. So you have to keep putting in work, you know, either with water coming out of the bottom of a dam or, you know, so hydroelectric or gas powered or whatever powered, you'd have to keep putting that in to keep spinning it. Is that what you're asking? Okay. No, it's a good question. It's just, you kind of do this so much and you get used to that just, you know, being the only way to do it. So you know, good to ask those questions. All right. Anything else on this page? All right. Alternating voltages and currents here. So voltages and currents in an AC circuit both average to 0. That's a problem, right? If you look at a sine function, like if you look at this, what's the average value here? 0. If you took calculus with me, calculus 2, you should know how to do this, right? Take our integral over this, right? And then divide by whatever interval we want. It's going to be 0, right? If I integrate from here to here, then the average over this one cycle is 0. The only way I'm not going to get 0 is if I don't go through a full cycle, right? If I just do a fraction of a cycle, but then that doesn't really happen because we just keep it going. So you're always getting, so it's going to always average out to be 0. Okay? So that makes it a bit of a problem when we want to talk about this. And you don't always just want to talk about the maximum either. So it turns out one of the best things we can do to talk about this, to give us more of an idea of a closer idea to an average, is the root mean square. And what that means is we're literally doing the root of the mean of the square. So you're going to take your positive and negative thing and you're going to square it. That gives you all positive things, right? That takes this, right? It takes that and turns it into this. You are then going to take the mean of it, the average, wherever it happens to be. Actually, technically, I should make it really close because it turns out for sines it's 1/2. And then, because we don't want the average of it squared, we take the square root of it. And so that brings it down like that. And so it ends up with like kind of a better idea of what the average is in there. The root of the mean of the square. Square it, take the averages, take the square root. You all ever done that in any of your math classes? All right, so that's your root mean square we're going to do there. So we usually just call it RMS, like voltage, current RMS, and voltage RMS. This is the RMS. So instead of just talking about maximums or an average, which would be 0, you find this, you square it, you find the mean, and you take the square root. Square it to get all positives, take the mean to get the average, square root it to then get it back down to the scale on more what we were talking about. So you don't end up with something that's like greater than whatever it is. So when you look, and this is an important idea, hint, 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 nudge, 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 wink, wink, wink for test coming up since I just made them and I remember what problems are on there. It's a very good idea to remember when you look at 120 volts for a house, that's the RMS value. That is not the maximum voltage you get. That's the RMS voltage. And so what we can do is start using our old relationships with either the maximum or the RMS and start figuring some of these things out. Okay? So like Ohm's law with max or with the RMS. So we're just looking at it a moment. Because at some point it is going to have the voltage. Like if it's going up above 120 and below 120, and that's the RMS, it has to be 120 at some point. So at some point, like Ohm's law will hold for 120, right? When it's actually at that 120 volts, then this will be what it is. Okay, so let's take a look here. We can calculate the power. So P equals VI, which means it's I squared R. And we can substitute in for I, which is I squared, I max squared times the sine squared then of omega t times R. And then we can actually average it. all right, our average power is going to end up either being 1/2 of the maximum squared, or it's just the RMS squared. You see that down here? This for average or this. So what this essentially tells us is that it turns out that our root mean squared is related to the maximum by 1 over the square root of 2. Because it turns out if you square that function and then take the average of it, you're just as much above as you are below. You end up with that 1/2. And then when you take the square root, you're taking the square root of that 1/2. Okay, where is that? That's got to be in here. Did I miss it? So essentially what we can say is V RMS equals 1 over the square root of 2 times V max. And the same thing over here for I RMS, 1 over square root of 2 times I max. Okay. And that's just the nature of the root mean square of a sinusoidal function. Electrical fires can be started by improper or damaged wiring, causes too much current, and you end up getting too much heat and it makes a fire. We used to have fuses in a house, and you have fuses a lot of times still in cars or in like Christmas tree lights and things like that. It's a little piece of metal that is designed that if it reaches a certain temperature, it will just suddenly melt and break. And so as long as it's below that temperature, then it lets current flow. And the idea is then that if your wire starts drawing too much power, like say you hook too many of those Christmas tree light lines up together, right? You're not supposed to hook like 50 of them together. You're only supposed to do a couple. It'll start drawing too much current. The wires will start getting hot and it'll be a fire hazard. But they have those fuses, and that fuse will heat up because of all the current going through it. It'll melt a little, and then it'll break, and then it'll shut the power off to it. So it's a safety feature, these fuses. I've seen people talk about, they had a fuse blow in their car, so they just replaced it with a penny. Well, that's not a good idea, because the fuse probably blew for a reason, because something was broken and overheating. And then you put a penny in there, and that penny's not going to melt and break. And then whatever the other thing was that was malfunctioning and overheating you have a very good chance of that causing a fire. So don't do that kind of a thing. Fuses are specifically designed to break after a certain amount. So you can have like a 2 amp fuse that'll, if you go over 2 amps, it's going to break. It'll heat up too much and break and stop it. So it'll limit and make sure it's a safety thing. Now in houses, what we have instead are circuit breakers. And what these things do is they're essentially 2 pieces of metal, and they're like welded together like this. And then they each have a different amount that they bend when you change their temperature. So if the top one will contract more than the bottom one, what happens is this top one contracts and it'll make the metal curl, right? Because the inside of the circle is shorter than the outside of the circle. And so if it starts to, if it starts to heat up and the outer one expands more than the other one, it curls. And so if too much current goes through, what it'll do is it'll curl off and break the circuit. Right? This used to also be how they timed lights. Like your garage door light would stay on for a few minutes and then go back off, because they'd run electricity to that wire. It would heat up and it would bend and it would curve up and break and complete the circuit. And then once it cooled off, it'd slowly go like that and then just disconnect. And then it would go off. And then when you turn the garage door, it would heat it back up and make it connect. And this is kind of doing the opposite. This is connected, and as it heats up, it makes it come off. And your circuit breaker can trip. Well, the nice thing about that is you can reset them. With the fuses, they break, you have to replace them. Now we just flip the circuit breaker, right? If you accidentally plugged in too many devices in your kitchen, you had too many things running, and then it cut because you had too much on that one circuit. Okay. Another thing we have are the ground fault interruption circuits. Those are the GFCIs that you usually have now in houses. And they're those ones where you look on the little power outlets, and they're usually like the outlets are all rectangular, and they have a little reset and set buttons in the middle of them and a little light on. Okay, so those work a little different than the fuse boxes. You see, if you start to electrocute yourself, if say you have a 2 amp fuse in there and you start to electrocute yourself on 1.9 amps, well, 1.9 amps, I believe, is more than enough to kill you. So you could sit there and just be getting electrocuted all day long on that, and the fuse would never trip, or the circuit breaker would never break. So what we also have now, and I think this is also just so super brilliant, is you have this thing. And the long and short of it is, current goes in, and it goes through here and creates a circular magnetic field, right? So if we're looking at this, the current going to the right creates a magnetic field that's wrapping around this way. And so it would therefore magnetize that little coil there in one direction. The current coming back out is going to create a magnetic field that's pointed the other way, that's curling the other way. And so what are they going to total out to be if the current going in is the same as the current going out? Zero. And so essentially what happens is, as long as the amount of current that's going into your device is also the same amount that's coming back out, it means that the amount of magnetic field through this sensing coil is zero. But what do you think happens if, like, say your device breaks and it shorts out and current is going into it, and then maybe like into you and not coming back out through the circuit? If that happens, then you get this occurs. You only have magnetic field going one way, or at least more going one way than the other. This thing then senses that there's a flux in there and reads it as, oh, I've got current going in but not coming back out. Somebody's getting electrocuted, or something's getting shorted, something's going to cause a fire, and it will flip off the circuit. It'll cause it to break. All right, so usually if these are tripping, it's because something has a fault in it. It's got something wrong with it. These are not usually the ones you want to just do it. Something shorted out and something caused it to trip. So these aren't the ones you necessarily want to just say, all right, well, I just will run these one at a time instead of all at once. I won't run the microwave and the stove and the refrigerator and the blender and the mixer and all at once and just flip my power switch back, flip my breaker back on. Something's broken. So be careful with these and whatever you were using that caused it. Okay. Next, AC capacitors in a circuit. So when you first turn on a current into a capacitor, it acts like it's not even there. Remember that? It acts like a short, like it's got zero resistance. As current starts to build up on it, it starts to decrease. As charge builds up on it, it starts to decrease the amount of current that can flow. The voltage goes up and the current goes down. Okay, and so here what we have is the root mean square of the current and the capacitor, and we have it related to the frequency. So if you look at this right here, that's an important one. The root mean square of the current is equal to the angular frequency, which is 2 pi f, times the capacitance times the root mean square of the voltage. Okay? And that should make sense to you because that omega is per time. So C times V is essentially charge, and then per time is current. Okay? So that's a very important one. Notice here that the higher the frequency is, the more current you're going to get. You see that? The higher, the faster we switch it, the more current we're going to be able to get to go through this capacitor. Why? Because we're switching it so fast, the capacitor is not having a chance to fill up. And so therefore it just continues to act less and less like a lower resistance, because you switch it before it gets to ramp up and fill up. right? You're just switching it and emptying it so fast that it never fills up and it starts to act like a short. And so high frequency signals will be able to send a lot of electrical signal through this. Low frequency ones will not, because it'll start to go up and the capacitor will fill up and it'll cut off the current. And then it'll start to go the other way, and then it'll start to try and discharge it. And then it'll, and then it'll slowly try to charge it and slowly try to discharge it. And so it's going to not be very, you're never going to get as much current going through it once you get it going. Here, rather than talking about resistance, we talk about capacitive reactance. It's essentially playing that same role. What is the word? Analogous? Analogous? I don't know how to say that one. What is it? Analogous. That word. It's that to the resistance. It's the alternating well, kind of the alternating current version. The real alternating current version usually talk about is impedance instead of resistance, but we're not going to get into that. So you can end up with this. And so instead of V equals IR, it's like V equals I XC. Okay, and that's our capacitive resistance. Notice it just equals 1 over omega times C. So if you know the frequency of your signal, it depends on both the frequency and the capacitance. The larger your frequency gets, right, the smaller your reactance is going to be. It doesn't have a chance to react. Does that make sense to y'all when I say that to you? About it being so fast that the capacitor can't fill up, and so it just goes right through, and then you switch it before it fills up, so you start emptying it immediately before it even got very full. Yeah. Yeah, the frequency of the signal. Okay. We typically use this, like say I had a speaker here, let's say, and let's say this is a speaker like this, and I had my source over here, like that's my radio, and I wanted this speaker to ignore any of the high frequency ones. So say this is a subwoofer. What I would do is attach a capacitor right here, a big capacitor. And then what happens is I'll end up with, coming from my radio here, I'll have high frequency signals and low frequency signals, depending on what sound it is. The low frequency signals, those are your low sounds you want to go to the subwoofer. The high frequency signals are the ones you don't want to go to your subwoofer because they're the high pitch sounds. Well, the high frequency signals see this capacitor as a short, and they see the speaker as a resistor. So they're going to go this way. They're going to cut through that capacitor. The low frequency signals, right? They see the capacitor as a resistor because they start filling it up. And so they see it as a resistor. And so they split and they go up and go through the speaker because the speaker is the easier way to go for them. So just by doing this, you have split your signal. Okay. And I could take this part right here and send this over to my high pitched little tweeters or whatever. And you can arrange this such that you can split your signals up like this. Okay. They're called high and low pass filters. Does that make sense? A little bit, maybe. Get rid of that. Sorry. All right. And then notice the reactance also has a unit of an ohm just as well. Okay, it's basically playing that role. If you look at a capacitor in an AC circuit, you see our phase diagram there. You can see that the voltage lags it by 90 degrees. When your current is at a maximum, your voltage is going to be 0. So in other words, when the current is turned up this way and at a maximum, what color is that? Brown? I don't know. The voltage is over here and its projection is 0. Like in that situation, because your current is a maximum when the capacitor is totally uncharged, and just whatever first current you send in can just hop right on there with no resistance to it whatsoever. As the current starts to fill it up, this will rotate, the current will start to decrease, and the voltage will start to increase, right? Until you reach the point that the voltage is now pointed straight up and is a maximum, and the current has dropped to 0. So they are off by 90 degrees from each other. Okay? They're out of phase by 90 degrees. And you can see that in this picture right here too. When the current is at a maximum, voltage is at 0. When the voltage is at a maximum, the current's at 0. Right? Current's at a negative maximum, voltage 0. Voltage at negative maximum, current at 0. Okay? Any questions on that? And that's it. I'm not going to go past there. I did the example problems that went with this. In fact, I even want to show you like this first one, super simple. All right. They tell you the typical household circuit is 120 volts. That's the RMS. So what is the maximum or peak voltage? It's just 1 over the square root of 2 times the maximum voltage, which means the maximum voltage is square root of 2 times the RMS voltage. So that one, very simple little question there. No, we'll stop right there. Do you want me to do the RC circuits next time? I mean, I guess I could instead of reviewing. That's the relationship between that. When we did the root of the mean of the square, right? Which was, I wrote it down back here, didn't I? I wrote both of them. Yeah, right there. Root of the mean of the square. So I guess the square can remind you of the 2, and the root can remind you to take the square root of it, or something. I don't know. If you remember your calculus 2, you can actually go through and take the average of the sine squared function, and you will get 1 over the square root of 2. Like you'll get that square root of 2, it'll show up. Feel free to try it. I know some of you can do that, or at least you used to could do it. Okay. This one, here we're given just a few little things to do. So an AC generator has a maximum voltage of 24 volts and a frequency of 60 hertz. It's connected to a resistor with a resistance of 265 ohms. Find A, the RMS voltage. So that's the first part I did, which is again just using that relationship. The RMS voltage is 1 over the square root of 2 times the maximum. So that's just 24 volts divided by the square root of 2, which is 16.97 volts. The RMS current in the circuit. So here I just used Ohm's law, but I used RMS for the voltage and for the current. And so IRMS is just V over R, which is VRMS over R. So that's that 16.97 volts from part A divided by the 265 ohm resistance. And that's 6.4 times 10 to the negative 2 amps, or what is that? 6.4 centiamps, or 64 milliamps. Next, I want to do the average and the maximum power dissipated. So the average power, remember we did right back there, was based on, where did I do that? That was, where did I do that average power? Right there. The average power is based off of the root mean square of it, or 1/2 of this, the maximum there. So I use that right there. P average is I squared R, but I RMS R. And so then that equals that. I could have also used P average equals V RMS over R. Either one of those would have worked since I have both those things. Then over here, I said P max equals V squared max over R, since I have V max, and I went ahead and just plugged that in, didn't it? I could have used the other one that was the 1/2. So you had a few options there. I could have used the 1/2 I max R, but I went with that. And so these are the results you get. Any questions on that one? Don't overthink this section, these sections. All right, here, this one required me to think about the phasor diagram. So here it says, consider a circuit with an AC generator connected to a capacitor where the capacitance is 50 microfarads. The maximum current is 2.1 amps and the frequency of the generator is 60 hertz. At a given time, the current in the capacitor is 0.5 amps and increasing. What is the voltage across the capacitor at this time? I don't know what time it is. And in fact, it'll repeat. There will be multiple instances where this occurs because it's going to repeat, right? So if I let this run forever, it'll just keep happening in an infinite number of times. So when I looked at this, I said that Vmax was Imax times the reactance. And then that tells me that Vmax is Imax over omega C, because that's what the reactance is. And so Imax is just 2 pi, Vmax is Imax over 2 pi FC, since we have the frequency. You can then solve that, and your maximum current is 2 pi FC times Vmax. Now, looking at our Imax, I know that at some point, it's going to have just a current output of 0.5 amp. So I drew this picture up right here, and I said, okay, I'm going to say this is my Imax. It's going to be at some angle theta, which is omega t. And when that happens, this is essentially going to be 0.5 amps. So I made it into a right triangle, and I came over here and I said the sine of that angle of theta for the current is your, if you look at this, this is really like over here. It's opposite over hypotenuse. So that's going to be IT over Imax. That's just definition of a sine from a triangle, right? And so then I solved this for theta. And so that's the arc sine of I as a function of t over Imax. I know that the current at that time is 0.5 amps. So I plug that in, divided by the maximum 2.1. So I just did the arc sine of 0.5 divided by 2.1. And that told me what the angle was for the current. You get that? Just did it geometrically. Now, if I know that that's the angle for the current, I know that the voltage lags behind it by 90 degrees. So if you look at my picture, you can see I drew this red one in, this red guy right here, that's the maximum voltage. And I said, okay, if I go over here, it's 90 degrees to what the other one was. That makes this angle right here 90 minus theta I. And if that's 90 minus theta I, then this angle right down here is just theta I again. It's the same angle. So the angle that the current is making with the x-axis is the angle that the voltage is making with the negative y-axis. Do we all agree with that? I didn't have to have done that. I could have used the 90 minus theta, and I could have done that and used sine, but I'm going to end up, I believe, using cosine here. So I came over here and I said, all right, definition of cosine is adjacent over hypotenuse. So that's what I did right there. I said, all right, cosine of that angle is the V of t over V max. So the magnitude of V of t is V max times the cosine of that angle. V max is I max over 2 pi FC times the cosine of the angle. Plug in all my numbers, and I get 108 volts. Now notice this is the magnitude of it. You then have to refer back to your picture over here and note that that projection for voltage is pointed down. So it's negative 108 volts. Because you could have made it, you could have gone with the 90 minus theta and had a negative angle, in which case it wouldn't have been the absolute value of it. But I made it geometrically simpler and then just, you know what I mean? I used concept to avoid a little bit of math there. But you could have just purely done the math with the negative angle and it would have worked out for you. All right, any questions on that? And that's the last one I did. Okay? No other questions? That is it. Wednesday, any questions you'd like me to go over in class on Wednesday for the review, please send them to me. The more you send me, the better the review will be. If you have nothing to ask me, I will just assume that's because you know it all. So, you know, the only thing I can do if you don't ask me questions is come in here and try and talk about everything we've done through the other chapter in these two sections and try and fit something that took me several days to cover in class, all compressed into one class. You know what I mean? That doesn't work. The best thing is for you to send me questions and come with questions to ask me. It helps if you send them ahead of time. That way, just in case I don't get stuck on something and end up wasting a minute or two thinking about it, I can have it done ahead of time. All right? No lab. If you want me to make up one for you, I guess I could. Okay? Y'all have a great day. See you Wednesday. They're done. They're already posted. Aren't they? Look and make sure. I thought they were. Please do.